In this video, I'm going to go through 4 really quick ways of how you can use the Pythagorean identities. So these are the main ones, and the proof of these can be done later on. Just to note that sometimes we write cosecant as CSC, so that's the short for it. So the questions are as follows. They're going to be in this format where you're given an expression or an equation, and then you need to simplify the expression where this letter is used. But we need to use the Pythagorean identities, or we need to keep them on the side in case we need to use them. So root of 1 plus t squared, well, t is just tan theta, so that is 1 plus tan squared theta. And I can immediately look at here and see that tan squared theta plus 1 is just secant squared theta. Now, it is possible to actually solve this without using this identity and like go through the full algebra of like converting this to the tan identity and then making the denominator the same, so on. But the whole point of having these is that, well, we don't need to go through the algebra. We have a method. We've already done the algebra in this. So I can just replace this with secant square theta, and this is something being squared. I'm taking the square root, so they cancel each other out, so I'm left with secant square. You can leave the final answer as this. If you really want to, you can replace it with cos theta, but this is acceptable as well. So something similar, but this time it's t over 1 plus t squared. Well, we know what this denominator is. We just found it as secant theta, so not secant squared, just secant theta, and then the denominator is just tan theta. To simplify this, if you're quick with the algebra, go for it. Otherwise, I'm going to go through the tiny steps, just in case you're still not comfortable with what secant theta is. So this is tan theta being divided by secant theta, and I can use the definition of either to simplify it, because you need to simplify it to its simplest form, and neither of these are like expressions on their own. Tan theta is a representation of the ratio of sine theta over cos theta. So I have sine theta over cos theta divided by, well, secant theta is just 1 over cos theta. And then I could use the rules of dividing fractions, change the sign, reciprocate the second fraction. So I have sine theta over cos theta times cos theta over 1. And then I could cancel these out, and I get a lovely answer of just sine. So this is the simplified form. Okay, so again, we use the previous results for this. One more example, we have a new expression. We have x equals to a sine theta, and I need to simplify this expression. So I'm going to go and square my terms. This is squared minus a squared, and this a and sine theta are being multiplied by each other, which means I'm allowed to spread this square into each one. Remember, if it's plus, you have to do the whole long expanding the brackets. I know this seems like a stupid advice to give right now at this level, but students do forget. Only because of these two are multiplied can I actually spread the square. Spread the square is an informal word, but there you go. And then minus a squared. Looks like here you can't really use much, but actually there's an a here that you can factor out, an a squared. So I have a squared sine squared theta minus 1. And this is now actually a rearrangement of the main Pythagorean identity. So I could take this, rearrange it, because remember the main Pythagorean identity you can rearrange in many different ways. So this is how it's actually useful. So I can write it as cos theta equals to 1 minus sine squared theta, and then kind of replace it here. So I can get, if I take out a negative instead, and that will flip my signs. So I have sine squared theta. So remember, if you multiply out, you actually get back to here. You can double check. And so I can replace whatever is inside the bracket with the cos squared theta. So cos squared theta, and so I get so we just expand out, and I'm going to get a squared theta cos squared theta. And that's kind of the final answer. You keep as that. So yeah. And the last question, we have y equals to b cot theta. So remember that cot theta is 1 over tan theta. The way to remember these is to use the third letter from each of the reciprocal trig identities. So I'm just going to rewrite whatever I have. Sorry, this is meant to be b squared. So b over root of b squared plus b cot theta squared. So if I spread out the squared that will go into this whole thing, it's going to be b squared cot squared theta. And I could do the same thing that I did on the previous slide, which is take the b squared out. I can factor it out. So I have b and then 1 plus cot squared theta. Sorry, take a b squared out. So with the square root, whenever you're multiplying two things, a times b, you can always spread the spread the surd, so it goes to a and then it goes to b. So the same thing happens here. I have a video on surds in case you need a recap on that. So b divided by root of b squared, root of 1 plus cot squared theta. And then I have, this will simplify to a b. I mean, you could have easily spotted this whole thing from here. You don't need to go through all these steps. And then these two will cancel out. And what I'm left with is an expression with 1 plus cot squared theta. And cot, 1 plus cot squared theta is basically cosecant squared theta. Cosecant, however you want to pronounce it. So we have 1 over cosecant squared theta. This whole thing is square root. Square root and a square, they cancel out. So I'm left with 1 over cosecant theta. And cosecant theta is basically cosecant theta is 1 over sine theta. So I'm taking the reciprocal of this, which is basically the reciprocal of this, which will give me sine theta. So that's my final answer. Hopefully these videos were helpful, and try to watch the next set of videos where more of these expressions are used.